How is the Jacobian matrix used in robotics? Imagine trying to control a robot arm so precisely that it can paint a tiny detail or assemble delicate parts. How does it know exactly how to move each joint to get the end of the arm where it needs to be? That's where the Jacobian matrix comes into play. It's like a translator that connects how fast each joint moves to how fast the robot's hand or tool moves in space. In robot kinematics, we deal with how a robot's joints and links are arranged and how they move. Each joint has a certain angle or position, and changing these affects where the end effector, the part that interacts with objects, is located. The Jacobian matrix takes the velocities of those joints and tells us the resulting velocity of the end effector. So, if you know how fast each joint is turning, multiplying those speeds by the Jacobian gives you the speed and direction of the end effector. This is super helpful for tasks like welding or picking up objects, where precise movement is key. The Jacobian is built from the partial derivatives of the robot's kinematic equations. These equations describe how joint angles relate to the position and orientation of the end effector. Think of it as a map that shows how small changes in joint angles lead to changes in the position and orientation of the robot's hand. When you multiply the joint velocities by this map, you get the velocity of the end effector in three-dimensional space. But the Jacobian isn't just for movement. It also helps identify singularities, those tricky spots where the robot loses some ability to move in certain directions. When the Jacobian matrix becomes singular, it means the robot can't move in some directions or might behave unpredictably. Detecting these points helps engineers avoid problems and keep the robot working smoothly. For robots with more joints than necessary to complete a task, called redundant robots, the Jacobian helps find the best way to move. It allows us to optimize the path, improve accuracy, and perform complex maneuvers. It's like having a control panel that shows how different joint movements combine to produce the desired end position and orientation. The Jacobian also plays a role in force control. When a robot pushes or grips an object, forces are applied at the end effector. The Jacobian helps translate those forces back into joint torques, which are the forces that move the joints. This way, robots can gently handle fragile items or apply just the right amount of pressure. For robotics engineers, understanding the Jacobian matrix is essential. It supports designing algorithms for motion planning and real-time control. It's also used in advanced techniques like machine learning to make robots smarter and more adaptable. In short, the Jacobian matrix is a key tool in robotics. It connects joint speeds to end effector velocities, helps avoid problems with singularities, optimizes complex movements, and supports force control. Mastering it allows engineers to build robots that move accurately, smoothly, and safely in all kinds of tasks.